Okay, so here's another video regarding the motor effect. You might have seen a video of my electric eraser. Okay, there are no other motors in this picture, right? Only speakers. In fact, here's a couple dissected speakers. I've pulled the magnet off the base of the speaker, and what remains are the wires that make a connection to this piece of wire. The whole idea behind the motor effect is simply that a magnetic field is able to influence the current in a loop of wire by exerting a force on it. You might think of the equation F equals BIL. In this case, the force doesn't cause the coil of wire to rotate like it does the armature in a motor. In the case of a speaker, the force simply either pushes or pulls on the coil. Another motor with the same design. As the diaphragm is being pushed in and out, that's just due to the interaction between the magnet and the coil of wire. We'll probably start referring to these coils of wire as solenoids. That's the typical name for this shape, this cylindrical tight coiling of wire. So there's another solenoid on this one, but the magnet's still intact. Now I can pull it apart and show you the solenoid on this one, but when I put it back together, this one is in the presence of a magnet. Right now it's connected to an AC power supply. Before we get there, let's see what happens when we connect the speaker to a DC power supply. Current will only flow in one direction with DC, so when I connect it here, all we get is a push, and the speaker cone gets pushed upward. If I put it back together and reverse it, well, you're not going to see anything because it's just going to pull it, but it's already as far down as it can go. So maybe if I were to lift it just a little bit with my hand and connect it, yeah, you can see it pull it down out of my hand. So if we want to produce a sound wave, what we need to do is compress the air and then rarefy the air and compress the air and rarefy the air as the speaker cone vibrates quickly. And I don't think I can move my hands back and forth fast enough to make that happen. So we're going to connect it to an AC source and let this power supply do it. I'm not sure what frequency it's going to be set at when I first turn it on. Let's see. Ooh, very high frequency. This cone is moving up and down 10,000 times in 1 second, if you can believe that. As long as it's somewhere between 20 vibrations per second and 20,000, we perceive it as some audible sound. So this is down to just over 100 hertz, 100 cycles per second. Let's just get it down to single-digit vibrations per second. Reduce the amplitude some. Oh yeah. Now we can see each distinct up and down push. That's sort of the frequency at which a panting dog breathes, huh? Let's get it down to just about 1, and we can simulate something like a heartbeat. How fun is that? All right.